Hello and welcome to this new video. Today we are going to talk about the Linux kernel 6.16, TDX performance improvement, a bunch of new features, and even a hint of drama coming up. So let's take a look at the note that Linus left us. So Linus says that 6.16 got pushed out as planned without any issue. Now the only little thing that he has to say is that 6.17 will be a little bit more hard for him. So the merge window happens at the same time as a wedding and a big birthday. So of course it will be kind of an issue because he has to travel a lot within that time frame. But apart from that, we should be good to go into the features. So let's start with the biggest feature of the day, which is KVM now being compatible to host TDX VMs. Now let's just explain that a little bit. So we're talking about the Intel Trust Domain extension, and it is a big thing for confidentiality. Now, just to get started, let's go into a bit of history, right? Let's put a little bit of information here. So for a long time, it has been the job of Intel, AMD, and all of the other players to try to make executing stuff on their CPU as safe as possible. And by that I mean that it may just happen that some software or some VM actually needs to have some things hidden from the host, meaning that even if the host wants to get some information, it cannot. Now, how is this enforced? Traditionally, you would use something like SGX, the software guard extension, which allows you to encrypt a program's memory. You could also use something like the multi-key total memory encryption, MKTME, which is used to encrypt the whole memory of a VM. So those solutions would be a good starting point to actually hide something from the host or from the operating system itself. Now, the game has changed because we now have Trust Domain Extension. Now, Trust Domain Extension is the logical extension of all that, right? We want our VMs to be fully separated from the host. Now, how do we do that? The way that we do that is inside of our CPU, we now have TDX chips. So those TDX chips are there to manage the VM for us. So when we have a VM that uses TDX, the memory is encrypted through the TDX chip, the communication with the host is done through the TDX chip, and the TDX chip will enforce the memory separation between the host and the VM itself. Thus, it is impossible for corrupted software or malicious software to influence the VM other than, of course, shutting it down, right? Besides freezing it or pulling the power from it, there's nothing that the host can do to the VM. So this is a big change. It was possible to have that TDX feature from some cloud services, but now everybody can use it as long as you have a CPU compatible with it through KVM. And this is truly the feature because you shouldn't have to trust Google, to trust Amazon, or to trust whoever your host is. You should have to trust Intel, AMD, and whoever provides the actual silicon. Those are the people that you should have to trust, and this is exactly the statement that Intel is saying right now, is pretty much you don't have to trust the host, you can trust the chip that we produce. And this is great. It ensures that nobody is snooping around and is making things that really shouldn't happen with your machine. Now let's get into the second feature of the day, which is ext4. Well, it's not actually a feature, right? It's a performance gain. We have 37% improvement on large sequential IO workload. So let's just open up the camera a little bit and talk about how this is actually done. So traditionally inside of the ext4 code and most place inside of the kernel, we are using for memory pages. So those little things. Now, the big issue with pages is that when you want to transfer them, when you want to put them as read-only, you need to do it page by page. So this is very slow process when you have a lot of page. So for example, if I want to put this read-only, I would have to put a post-it on each page. Very long, not efficient. Now, the way that ext4 and a lot of other subsystems inside of the kernel do to optimize is to use folios. So folios, as their name suggests, allow you to bundle pages inside of them, and instead of actually going page per page to be able to put it in read-only or transfer it, you can just put a post-it on the folio and you're done. So read only the folio, all of the page inside of it are read-only. So this allows a bunch of performance gain when we're talking about large files or large transfers. So this is very, very much what we want inside of the kernel. Now, let's be honest, the big reason why we see that with ext4 is because ext4 is a fairly old file system. When we see the newer file system, we can see that they are already built with that inside of them, right? They don't have to do the transfer to folios because they're already using folios. So this is a bit of a ext4 issue, but it's still good to see that they're taking steps to upgrade and to make sure that we have that extra performance. Now, while I have the camera open, let's talk a little bit about Kent Overstreet. Yes, the creator and main dev of BcacheFS, because he's been in the news lately. He's been in the news, and right now I'm going on a crusade. I'm going to kick Kent Overstreet. No, I'm joking. Kent Overstreet has been kicked from the kernel. Now, the big reason why he's been kicked from the kernel is because he has added a feature inside of a release candidate. Now, this may sound like not a big thing, but when we produce the kernel, there is a time for everything. So there is a merge window, which is opened right after the release of a new kernel. So right now, if you're watching the video soonish, well, within 2 weeks of its release, you are inside of the merge window. That means that if you are a kernel dev, you would be able to send a new feature and it could be accepted inside of the kernel. Now, if you wait after the merge window is closed, it becomes release candidates. Now, release candidates are there to test and fix problem. They're not there for a new feature. We don't have infinite testers. We don't have the capability to read even all the code that goes into the kernel, besides the developer that made it, of course. So we need some time to test and make sure that there's no issue with the new feature, and everything that's getting added to those release candidate is only fixes. So putting a new feature here is a very bad idea, and Linus did not like it. So Linus pretty much blew a gasket, said to Kent, "You're done, that's enough, you're getting out of the kernel next release." So for this release, 6.16, we have the best version of BcacheFS that we could have, and next release, it will either be disabled by default between a broken kconfig, or it will be fully removed from the kernel. So the code might be stripped from the kernel. Now, I mean, this was expected. Even if I put my faith behind Kent in the last release, I would have really hoped that he would have continued on his good ways, but no. I mean, he seems to just not be the guy that is able to follow the rules of the kernel. The rules are there for a reason. We need to follow them. So that's what you get. I mean, the only person that I can really say good job on would be Linus himself, because Linus saw the actual good things that Kent could bring to the kernel, the positivity that comes with having a new dev and having a dev that is competent, because there's no doubt that Kent is competent. And he tried his best to put him in line, to make sure that he follows the rule, to be patient, because of course he trespassed that rule a lot of time. And no, I mean, we cannot accept this behavior, so good job on Linus. He did pretty much his job perfectly. I wouldn't have done it. I wouldn't have waited that long, but I'm probably a little bit happy on the trigger. Now, if you're a BcacheFS enjoyer, don't be too sad. I mean, Kent already did most of the work that he needed to do outside of his file system, so making a module for BcacheFS, or actually making BcacheFS outside of the kernel tree is something that is very possible. So there's no doubt that Kent will continue making his project. It's just sad. I think that it's a big waste that could be just solved by a good attitude. And it's very sad to see Kent pretty much blame everything from the ground, the grass, the sky, but his actual attitude, right? Because we don't have that problem with 1,500 devs that are like, no, Linus is the issue. If that was the case, I would be primed to accept what Kent is accusing Linus of, but he's just not the problem. There's one guy that has been working for well over an eternity with everybody, and there's the other guy that comes around and that's like, you're the problem. Yeah, that sounds a little bit dumb. Anyway, let's go to the next feature. So let's get to our last featured change, which is OpenVPN. Yes, a network change, folks. So we have OpenVPN DCO driver that was added to the kernel after its 25th revision. Now, why do we care? Why do you care about network, Mabel? You never care about the network. Well, I do when it's an 8-time the standard user space OpenVPN implementation. 8x speed up, my friend. 8x performance boost. Now, normally, you would use an OpenVPN implementation that is completely inside the user space, and this is probably a bit why it is slow. So now this was completely implemented inside of the kernel, and it is now way faster. So from now, we are pretty much waiting on the user interface to catch up and actually implement this implementation inside of their user interface, and then everybody will have an 8x speed gain inside of their usage of OpenVPN. That's great! So let's go into architecture-specific change, where we have x86 that now have a new kconfig build time optimization that enforce -march equals native. So this is how you let the compiler know to optimize for your CPU. So now you can put inside of the kconfig this option just to make sure that your compiler optimizes for your CPU. So this is really great, and I'm kind of surprised that it didn't exist yet. We also have some additional AES XTS cipher optimization for the AVX 512 processors, so 1 to 6% optimization. So we don't have an optimization Olympics level of optimization here, but it's still pretty great to see things getting faster. Now on AMD's side, we have AMD SBI that now has its own subsystem outside of the hardware monitor. So that means that we can now use AMD SBI not with the hardware monitor, right? Now, what is AMD SBI? So AMD SBI is a small 2-wire interface that's also called the Advanced Platform Management Link. It uses IC2 or IC3. So what it is used for is for a BMC, so for a computer, a management SoC inside of your computer, to be able to go read and manage your CPU features through that 2-wire interface. So you can, through the BMC, through that small computer for your computer, you could before use hardware monitor to see what was going on inside of your CPU, but now you can also use it outside of hardware monitor. So it's not only for that you can use it. So that's a great thing. Now, still on AMD's side, we have a new SPI driver that was added. Now, what's weird about this new serial peripheral interface driver is that it is linked to an hardware ID that when you look, we have no idea what it is used for. So if you look on Windows, we don't know what it is for. There's no driver for it even on Windows. So we have a new AMD hardware SPI peripheral interface that we don't know what's used for. Great! So you're going to see, because throughout this this presentation, we're going to have a little bit of secret features that are going to be unlocked in this release. So this may make sense in the future. So still on AMD, we have the BIOS option, request CPU minimum frequency, that is now honored by the AMD P-State driver. So when we're talking about CPUs, Zen 4 and newer AMD EPYC system, they have this BIOS option that lets the user set an initial lower CPU frequency limit. Now this can still be overrode using the scaling min frec sys FS file, but still, it is great that the AMD P-State driver doesn't just ignore it like it normally does, so great feature as usual. Now, since the Zen 1 CPU, so since 2017, AMD CPUs have been capable to report the cause of a system reset or a reboot. Now, this was not implemented anywhere. So here we are, it is now implemented inside of the kernel. So the kernel is now able to read and will read the register containing that information and output it to the kernel log using the x86/AMD previous system reset reason and then give the actual reason. So this can be useful for people living dangerously. Back in 6.11, we talk about the increasing support for secured VM service modules, which allow the VM to use features like the vTPM feature. Now, the vTPM, of course, is, as we know, a TPM is there to store secrets for your computer. So a vTPM is just a virtualized version of that, and that's managed by the CPU itself to make it safe. So this was merged, this was a host feature. Now we have the driver side for the guest. So now the guest can now use this feature that was enabled on the host side. There's been a lot of KVM changes this release and a lot of cleanup and fixes. Even on AMD's side, of course, we've talked about TDX, but on AMD, we now have support for the option allowed SEV featured inside of the virtual machine control block. Now, the virtual machine control block is the way that secured encryption virtualization, the way that SEV manages its virtual machine. So it's a little bit like, like the control panel for SEV. So this allows you to enable or disable some SEV feature for your guests. So you can choose to give the access of the feature or not, depending on those options. So it gives some liberty to the hypervisor to do its thing. While we're talking about KVM, let's talk about some KVM x86 code that was added, some generic code. We have the advertising for 2 new CPU instruction that was added, so now the user space can know that those instructions are compatible with a given virtual machine. We have the WRMSRNS, which stands for Write to Model Specific Register Non-Serializing. Now, the Model Specific Register is a little bit like the control panel of your CPU, so you can set some instruction there in order to tell it to either act in a certain way or another. So that instruction is there to write to that control panel, and non-serializing just means that it won't clear out the whole CPU pipeline in order to do so, because normally there is the same command but without the NS at the end that allows you to do the same, but it will wait to clean the pipeline, make sure that all of the buffers are empty. So this is why it's called a serializing instruction. Now we also have prefetchy, which is an instruction to prefetch CPU instruction inside of the iCache of your CPU. So inside of your CPU, you have some cache dedicated for data caching, and you have some cache dedicated for instruction caching. That's called the iCache. So that iCache is fed through commands like prefetch I. Now let's talk about Intel with their support for the Advanced Performance extension. Now, if you remember that from somewhere, it's because we've talked about it last release, and last release they were doing the initial work on it, and now it's fully supported. Now, APX allows to have more, it doubles the quantity of register for your compiler or for any task to use, so this can be used to optimize especially compiler tasks. So this is very great for performance. Now, while I'm at it, let's just talk about the 5-level paging that is now unconditional, so it cannot be disabled. Now, this is, of course, not Intel specific, but most kernels, most config of the kernel that are public right now use the 5-level paging that you need it or not. So there's no real reason to use the 4-level paging. So now by default, it uses the 5-level paging. So that's not an Intel specific change, but APX made me think about it, so we take care of that real quick. Now, going back to Intel, let's talk about the Intel CPUs that now report outdated microcode as a vulnerability. So now you will be able to know that your microcode is outdated. Now, this also means that there's a big list of microcode being updated in the kernel for all of the CPU, so that the kernel can know. There's also the new Intel overclocking watchdog driver that has been added to the kernel. It has been brought by a Siemens engineer. Yes, not an Intel engineer. So it is used to, of course, report the stability issues that might happen with the CPU. But it is fun to see that other companies than Intel are actually bringing out features from Intel CPUs. Now let's also talk about Intel enabling the platform temperature control interface inside of the kernel that allows the user space to set a maximum temperature from multiple sensors inside of an SoC. So what this means is that you can say, hey, if that chip it gets a little too hot, or if that place on the computer or on the laptop gets too hot, I want you to bring down the power of the CPU. Now, the real reason why you would want to use it, of course, is if your BIOS settings are way too aggressive and you want to edit it. So if you want to have your own and the OEM setting are garbage, you now can using this feature. We also have support for the Speed Select Technology Turbo Frequency SST-TF. So the second version of that technology is now supported by the kernel. So SST-TF is used to be able to set a bucket of core that should go to a specific frequency, a specific turbo frequency first. So you can choose one bucket to boost their core, another bucket to boost their core a little bit later if needed, and a last bucket to be the last resort. So that's how this technology works. Now, the quantity of cores that you could put per bucket was limited to 256. So now they have blasted this limit because, of course, their latest CPU can reach over that limit of core. Now, Intel also updated their P-State driver with support for energy-aware scheduling for hybrid platform without symmetric multi-threading. So let's just bring some logic to it. So if you don't have hyper-threading on your CPU and you have a big little configuration of CPU, so you have a performance core and you have an energy core, especially with the current generation Lunar Lake or the next gen Panther Lake, you will be able to heavily prioritize the efficiency core. So as long as whatever you're trying to run can run on the efficiency core, it won't wake up the performance core. And that is needed because with testing, we know that the efficiency core will always be more efficient than the performance core. Even if it runs at 100%, it will still be more efficient than waking up the performance core. So that's why this is necessary, and this is a great upgrade inside of the kernel. So let's do a quick rundown because we've got a bunch of small features and I just want to run them down. So we have support for the Quick Assist Technology Accelerator, CAT, 6th generation. So the Gen 6 is supported by Xeon Diamond Rapid processor, so those will come in 2026. Now, what is the Quick Assist Technology Accelerator? It is a cryptography and a compression accelerator. So it is there to make sure that you can compress and encrypt faster. Good on us. We have Turbostat that now supports Xeon Diamond Rapids, again 2026, and Bartlett Lake, which should be there this year. It's hard to have information about it because those CPU are more industrial CPU. They're generally not for the general consumer. And we also have the audio support on Intel Wildcat Lake, which should be out either this year or 2026. Not much is known about this architecture, other than it is a very low power chip, so audio support for that. We also have support for the performance monitor unit found inside the next-gen Xeon Clearwater Forest due to come out 2026. So, of course, the performance monitor unit does exactly what it says. It monitor performance, so good on us. We also have the error detection and correction subsystem that now supports Alder Lake S CPUs and Raptor Lake S CPUs. Now you may say, what the hell is this? Alder Lake is 2021 and Raptor Lake is 2022. How does this even make sense? Now this makes sense because nobody is using ECC memory with those platforms. So of course the error detection and correction subsystem is there to manage your ECC memory, your error correcting memory. And those are consumer CPUs, right? They're CPUs that you would not normally see having ECC. So it makes sense that we're late on it. Now, something that is more insane is the fact that, again, in the error detection and correction subsystem, we now have support for the Xeon 6 Granite Rapid. That's 2024, guys. They just added the rework of the RRL register. So it just doesn't make sense. This CPU needs ECC. Well, needs is a big thing to say, but normally when you have a Xeon CPU, you're going to use ECC memory for it, right? So was it that it was not compatible? Was it that you could not use ECC with that Xeon CPU? Or was it that only a feature did not work? I'm kind of confused here. I hope that it's the latter. Now let's go into ARM, which enables support for the ARM Scalable Matrix Extension, SME. That was disabled in the past due to a bunch of bugs, but now is enabled on the few SoC that support it, because this is not really a popular thing to put inside of your CPU. Now, this may be like egg and chicken thing, right? Because if you don't have the capacity to use a feature in Linux, why would you put it inside of your SoC? But it's also something that is a little bit niche, right? We're talking about scalable matrix extension. This builds off the SVE and SVA2 vector extension. What you need to know here is this is for AI. So this is a specialized chip, a specialized part of your chip made for AI. So makes sense that it's not really that important, at least for now. And again, on ARM, we have lazy preempt, which was, of course, added in 6.13, now is supported by ARM64, so it joins all the other in having that lazy preempt support. Remember, in the kernel, there is multiple ways to do preemption when you're inside of the kernel. So preemption, of course, is to remove a process or a running thing from the CPU, from your core. So when you select a different type of preemption, it will inform how the CPU should handle taking the kernel off the core to make something else run. Now, lazy preemption is just a new way to do it. Watch the 6.13 video for it. I'm not doing the full explanation. Of course, we've got my favorite, LoongArch. So LoongArch now enables multi-core scheduler support. So this kind of baffled me. Does that mean that the scheduler really doesn't support being on more than one core at a time? This is insane. Of course, this is default in x86, but now is possible to be enabled on LoongArch. We also have support for MSeal. We talked about MSeal a bunch. It's a new system call that allows the kernel to actually freeze memory and make sure that it is immutable. So it's kind of a buffed read-only, right? So this is now supported by LoongArch. We also see support for stack leak, which is pretty much the kernel poisoning uninitialized values just to make sure that somebody could not mess around in there to try to infect the system. So this is a good protection to have. And we have the support for up to 2048 cores. God damn, that's a lot. Now let's go to MIPS. As we've discussed last release, MIPS is dead. But there's still people working on it, of course. We have EchoNet that works on router that have added one SoC, so good on them. But most manufacturers, of course, are rotating to Risc-V. Now, Risc-V has a big release today. We have the support for the get random inside of the VDSO. Remember, the VDSO is a library that every program from the user space can access while they're running. So putting things in there makes it faster than actually using a system call. Now, what's fun in the support for that, of course, that support has been there for a long time for a lot of architecture. It has been added initially in 6.11. But what's fun with this release is that we have a test. We have a test that actually compares VDSO against the system call and against libc. So, of course, we see that libc and the system calls have pretty poor performance, but we have a 16x faster performance with the VDSO implementation. 16x! Now we see why this was so important to put inside of the VDSO. Now, for Risc-V, we also have support for KVM that is now no longer considered experimental. So this is great for Risc-V. Now we also have support for MSeal. We've talked about it. We have more optimized RAID 6 recovery calculations that were added to Risc-V. We also have support for SBI FWFT. Now, what this means is, of course, SBI is for Supervisor Binary Interface. The Supervisor Binary Interface is a standardized communication channel that helps the CPU in S mode, so the CPU in supervisor mode, you can kind of equal that to kernel mode, to communicate with M mode, which is machine mode. So Risc-V CPUs have those different modes that can talk between each other. Now the SBI allows the kernel mode, the supervisor mode, to talk to the machine mode, and it can tell things like, hey, I want you to shut down the system. I want you to send that message between that core to that core. So you can have those communication done through the SBI. Now, the FWFT stands for Firmware Feature Extensions, allow the operating system, so the in S mode, of course, to control or ask features that are handled by the firmware. So here we can ask, is a feature enable or can we enable it? Now we can enable features like shadow stacks and more. So this is a great add to the Risc-V architecture. Now we also have a bunch of extension that we have support for. We have SV-inval, which is used for fine-grained TLB invalidation. So remember, the TLB is for translation look-aside buffer. It is a buffer that contains all of the address for your pages that you're currently using. So normally when you would want to invalidate a TLB entry, you would like to remove a page address from there, you would use sfence.vma. Problem is, when you use that, it is a little bit aggressive in the way that it does it. So sometimes it will invalidate way more than what you actually want to invalidate. Now, this SV-inval is it is a precision tool, right? So it will just invalidate what you want. So this, of course, can be good because if you invalidate a bunch of things that you will use like 5 seconds later, you're just wasting your time. We also have Zigbop, which is to prefetch some memory to the CPU. We also have Zaba, which stands for byte and half word atomic. It adds atomic operation for bytes and half words, so for, of course, 8 bits and 16 bits. We also have the extension from Sci5. So Sci5 is an American fabless designer of Risc-V CPU. They make their own extension. So we have matrix multiplication instructions. Yes, they really look like that. Those are pretty crazy things to write. But so we have those. So remember, matrix, think AI. And we also have FP32 to int8 range clip instruction. Again, we have a crazy name for it, but those calculation from a floating point 32-bit to an integer 8-bit are done throughout AI. So Sci5 is positioning their instruction strictly for AI. We now have support for them inside of Risc-V. Now we also have more hardware in the kernel. We have the SoftGo SG2044 SoC that is now compatible, but It is pretty much just a big brother to the SoftGo SG2042 SoC, but with 2 times the performance. If you're wondering, this is the CPU inside of the Milc-V or Milc-V Pioneer. So don't know how to say that, but that's a pretty well-known computer. Now let's go to the power architecture, which now has support for a 2021 feature back in 5.12. This is the config preempt dynamic. So this allows you to select your preempt mode as a boot option. So instead of setting it when you compile the kernel, you can choose it when you're opening your machine. Now let's talk about NVIDIA on the GPU side that now has support for their Blackwell and Hopper GPU. Now the Blackwell GPU are the GPU size of a motherboard, so those are big beast. And when we're talking about NVIDIA, we're talking more precisely about the Nouveau DRM driver. So we're talking about the open source side of things for NVIDIA. Now, if we go on the Intel side of things, we see that Intel is working on their Z3 integrated graphic to be launched this year. So yeah, we see more and more support here. We also see, similar to the 6.12, we see Xe GPUs having support for the fan speed. So in 6.12, we saw it for their older GPU. Now we see it for the Xe GPU that you can now see inside of the hardware monitor, the fan speed. Now we also have support for the link off between frames for their i915 and their Xe kernel driver. What does that mean? Now the link off between frame means that the eDisplayPort link inside of a laptop would close itself, would remove the power between long V-blank duration. So if there's nothing happening on screen or just a slow refresh rate, well, you can close that link, thus saving some power. So this is a great feature to have on those newer GPU, although the i915 are getting kind of old at that point. And last change for the GPUs and Intel side is we see additional Intel Battlemage PCI IDs added for future graphic cards. So we see Intel not giving up on their GPUs. Now on AMD's side, we see their work on AMD KFD, which is their computing arm of the GPU. So when you use AMD KFD driver from the kernel, you're using it for OpenCL, you're using it to do some processing other than graphics on your GPU. So that driver is now supported for Risc-V. So it joins x86-64, Power64, ARM64. So pretty much joins the big family loving that AMD KFD. Now, this is very great because AMD seems to be very popular with Risc-V machine. Now let's go into the file system side of things, where VFS now support a freeze option. Now, when we say freeze, this is used for suspend and hibernation. So most suspend and hibernation features are actually mostly done by the user space. If you use systemd, it is pretty much 100% done by systemd. So the way that it works is it's going to freeze one process one by one normally, and after that, it will tell the kernel to do its thing to actually suspend the machine. Now, with that VFS freeze support, what it does is it also gives VFS the ability to just freeze a file system. So make sure that the file system doesn't write or read. So this is very useful because sometimes it's hard to tell an actual program to stop doing things, right? It's not always just snap your finger and freeze every process running. Sometimes it's a little bit harder. So having that ability to make sure that VFS won't take any more orders, make sure that there's not corruptions that happen that wouldn't happen otherwise. Now let's switch to XFS, where we've talked in the past about support for atomic write. Now that was a big thing, but this was limited to 1 block chunks. So you could only do a atomic write when you would use only 1 block of memory. Now in this new release, you can actually have more than 1 block being written in an atomic write fashion. Now this is very useful, especially for database that DBs actually need that feature more than anything else, and it adds more speed. So we have a lot of DBs that actually use 16K blocks, 16 kilobyte chunks of memory when they work. So now XFS can fully utilize this feature because it can use it with database with that block size. Now for the network file system with NFS, the NFS server now support larger I/O block size. The default was 1 megabyte, but it can now be set up to 4 megabyte. This can give more performance for some user. So now let's talk about Fuse, where they have made some change. So in the file system in user space, they have increased the read directory, read dir, buffer, so that it is a little bit bigger, and this increases performance. There's also a whole bunch of small fixes that were added, of course, as usual. And in F2FS, let's just switch to them, they have gone the same way as ext4 and added more and more folios to their code. And same thing with BtrFS, more optimization, more folio use, so that's all great. But where we're going to talk a little bit more would be EROFS. EROFS can now use the Quick Assist Technology Accelerator, CAT, like we talked a little bit earlier, but of course it will be able to use the 4th gen or the 6th gen, whichever you have. So remember, EROFS is a read-only file system, so making it have better decompression performance is important. Now back with 6.12, we add the support for TCP zero copy receive to a DMA buff region of memory. So what that meant was that you could receive a TCP packet, so you could receive data from the network, and you could put it onto your graphic card or any other peripheral that you have that support DMA buff. So it would make things way faster because the CPU did not have to handle that packet, right? Now we have the same thing, but in the other side. So we can now transmit zero copy using the kernel. So TCP TX now supported zero copy. So you can take what you received and send it right back in a zero copy fashion. This, of course, improves performance a lot because you don't have to use a CPU to send things and waste your time processing it. We also lost support for datagram congestion control protocol, DCCP. So that was removed from the kernel because it was unused. This was a replacement for TCP and UDP, mostly used for things like gaming or voice over IP. So it tried to fix the shortcomings of the traditional ways that we would send data using timing constraint and a bunch of things, but it ended up never being used, so that's why it's here today. Now let's dip a little bit into hardware, where we're going to talk about Apple and their PCI controller. So we now support the Apple T6020 range of PCIe controller. So this comes with the M2 Pro SoC, the M2 Max, and the M2 Ultra. So this is, of course, all thanks to the, I don't know how to pronounce it, Asahi. Anyway, you see it on the screen. The crew. So thank you a lot to those people. Now, one change that has intrigued me was the fact that they managed to optimize the exit to user mode. So as you know, when you go into a syscall, you need to end up coming back from that syscall. So when you call a syscall, you go into kernel mode and then you come back to user mode. Now, there was some optimization that were done to that code to return from a syscall. And well, we see with a benchmark that was done with get PID syscall, which is a very cheap one. They ran it on different architecture, and they saw on Risc-V a 7% improvement, on x86 almost 3% improvement, on LoongArch it's 6%, and S390 an 11% improvement. Of course, they don't have that architecture, they probably used QEMU, but that's still great to see that we have some good performance improvement, and of course those apply across the board. All system call will benefit from that. But just so that you keep it clear inside of your mind, this is not something that that will affect you that much, because of course get PID, the syscall that is being used, is a very cheap one to run. It's not the a complex syscall, and if you have a complex syscall, it will take way more time to run than the actual improvement that we see here. But it's still a great thing. Another good feature is that you can now core dump over a Unix socket. So Unix sockets are created as a communication between processes. Now, a core dump happens when your program screws up a lot and dies, so you can now set your program for when it dies to forward things to a process so that it can be processed correctly. Now let's talk about GCC8, which is now necessary to compile the kernel. And I hear you here, but Maple, you told us last kernel that you needed 8.1 to compile the kernel. And yes, this is the minimal version for a lot of architecture, but depending on your architecture, that can change. The big news here is that we removed the pre-GCC8 fix in the kernel. That means that even if you wanted to compile with a sub-minimal GCC version, or if you add an architecture that still was compatible with something under GCC8, now it would not work because the fix are not inside of the kernel anymore. We also have reporting for soft and hard lockups and also RCU stalls inside of SysFS. Let's just describe a little bit what we're talking about here. So soft lockups are defined as a bug that causes the kernel to loop in kernel mode for more than 20 seconds. So this usually will block the user space from doing anything on that time. So this is, of course, not something that we want to happen. Normally, when you have a bug in this order, it's very bad, and it shouldn't happen in the production kernel. Hard lockup is defined as a bug that causes the CPU to loop in kernel mode for more than 10 seconds, and that doesn't give interrupts the chance to run. So this is even worse because in a soft lockup, you could technically still have an interrupt come in and just do its thing and then load back the bugged code onto the CPU, and you would waste your time there. But a hard lockup, it makes sure that nothing, truly nothing, will run in its place. So having some count for those is really important, and having it exposed makes the job of the devs way easier to see what triggers it or not. Now, an RCU stall is when the CPU loops in place for a bunch of stupid reasons. Let's not go into them, but RCU stalls are when your CPU loops and it shouldn't. So as you see, those are pretty core issues. They're not things that you and I will care about or look, but for a kernel dev, this is pretty important. And let's finish with Rust that gains more and more abstraction. We have more work in the DRM side of things, so the graphic side of things is being worked on, and we have more work on the memory management front. Here we see Rust growing, and having more and more every day, but no big flashy feature for today. So that's all for this video. Today's word will be RCU stall. So write RCU stall in the comments to show that you are an absolute unit. Now, of course, if you enjoyed, leave a like, leave a comment, do all the nice things that you normally do. And of course, see you next week. Take care.